So let's start. So first of all, thanks Nicola and Claudia and all the organization for inviting me. So today, as Nicola was saying, my talk is a little bit more into the methods. But it's very related to what actually Alex was saying before, but on another scale, right? So what I'm trying to convince you is basically that space counts when you study phenomena. You have to take into account the spatial component, right? Otherwise, especially in social, computational social science, missing the spatial bit can lead to like false basically results, right? So I'm going to show you what is basically the methodology to start from data. So get data, start from data, doing some descriptive analysis before, and then going a little bit more into the analysis part where you try to basically get some, study some patterns, right? Some emergence of patterns. Okay, so as Nicola was saying, it's not working. Of course, yeah, it's always like this. Now, yes, so I'm basically from Turin, where I'm an assistant professor. Turin is a city in the north of Italy. And then it was 2009, so I was a visiting scholar in Bloomington, where I met Nicola and Alex, so in the Alex lab working with Filippo Mensa. And there, actually, I met Nicola under a very different perspective. So that's the gangster Nicola. But please, so that's something that I want to ask you personally to ask basically Nicola about his Pope version. So to ask him how he became Pope. So he's the official.
Fake news.
This is the actual newspaper, so a real one. Anyway. So then I moved to my sabbatical. I went to Yahoo in Barcelona, and I moved a little bit. I visited also London and New York, and there I started to work on spatial data, so in urban computing, basically. And now I'm visiting often the Cambridge lab, where some of the people that basically I was working with, Luca Iello and Daniele Quercia, mostly, they are actually working in Untitled labs. Okay, so the objective of this class would be exactly to understand why spatial thinking is important and try to do a description of methodology to describe, visualize, analyze, extract patterns, and a little bit we probably won't have time to deal into the explain part. It actually is true that it's probably the most difficult but the most interesting, but I'll give you some pointers. So the goal is to basically let you fall in love with spatial analysis and mapping, but I think already Alex explained and nice visualization and why it's very important, the spatial component. So I'm pretty sure you are already in love with anything that is spatial. So a first example, let me give you a first example why spatial thinking is very important. And the first one, so this is our beautiful school, but imagine that instead of this, we changed it. And we moved all together in this very horrible cities. It's called Norwich in Siberia. Actually, it's one of the worst cities according to a study in terms of characteristics of urban environment and stuff like that. So actually, next time, I suggest the organizer they should, there is no internet, probably, but that's the complete site, so I help people doing it if they want. But basically, you can go here, and instead of, it should be a map that there is no internet, so the map of Siberia, and this is the place where we are going to do the social dinner and all the places we are going to visit. So, we are not going to see them. We are not seeing that, so you basically missed all the website. So I beat actually the real website. But my point is that, of course, moving from here to another place, you have completely totally different experience, right? In terms of many aspects, and social interaction is one of them, right? So you cannot even find a route, basically, from here to this very far city. So space, in this case, matters. But this is a little bit more serious example. So this, of course, any lecture in geography starts from this map, actually, one of the most famous map. This is basically a map made by John Snow for the epidemics in London in 1854. Basically what he did, he mapped all the occurrences of cholera, actually, that made like thousands of dead people, actually victims in London. And what he saw basically is around basically that area where all these deaths basically were clustering. So basically it was the first evidence that here, around here, there was a water pump. So basically the main idea at that point was that cholera was transmitted by air, actually, not through the water, actually. But this was the first, how to say, visual demonstration that instead of saying that this is something that transmitted by air, is something that actually transmitted by water. And this is because all the elements, all the death basically was clustered around the special area where the pump is now. So basically saved many lives with this, it changed actually the policy that London we used to use cholera. But anyway, so this is a more serious one. Here is another way, so for example, we want to study something that is common in sociology or demographics. You want to study the percentage of the population that is a certain race, let's say black people. This is a city by county. You can take any city, so this is Washington DC, I think. But anyway, so the point is that if you see here, this cluster, so basically what you can see is segregation, right? So basically outside in these areas you have a few percentage of black people while all the black people are clustered here. So there is a kind of segregation pattern in the space. So take all these counties, so the same value, and you shuffle, so basically you randomize, and then you basically lose the pattern, so there is no segregation anymore. So but the point is that if you plot the data, and you plot just a histogram, so by county, so the distribution is the same, right? So you cannot say, so basically you have the same distribution, but that lead to completely different observation if you look to the space, right? Here segregation, here not segregation, right? But using only descriptive analysis without the space component, you lose basically all part of the information. Okay, so the other reason is that, of course, location data is pervasive, and we saw before many examples of that, data about mobility, Twitter data, social media, everywhere, every day, we basically create data that has the spatial component inside. So that's the other very important reason why to use that. So let me just go very quickly, because so as a computer scientist, I approached the problem when I started working on this stuff as a computer scientist, so dealing with data and technicality and stuff like that. But then I started a little bit to zoom out, and actually there are many disciplines that study already the spatial component, of course, and the first one, and the biggest one actually, is geography. So as you can see, basically, there are many definitions. The one I like the most is that geographers are basically master of processes. So you have a process going on that produces a certain effect. It goes through space and time, right? There is not only space, of course, there is also time involved, right? And these are very coupled. So you cannot study space without time and vice versa, actually. So the processes goes also through time. So this is an example, for example, in geography. So you take a map. This is the, so this is a volcano, St. Helens in the United States. It was, if you study the map at this point, stage in time, you see the volcano. Here are like some urban settlement here, and then an event happened. So you study the same environment. This is the same picture, the same location, but a different time, so after the eruption. And of course, the phenomena that you study is completely different, right? So it depends on when you study also a certain phenomenon in space, so you cannot discard also the time component, which is actually very important. Okay, so let's go very, very quickly here. So you have geography, basically the physical geography. We are not going to talk about that. It's very old discipline, but we are talking a bit more about the human part. So this is actually a branch of social science, and it studies many phenomena in space. It could be related to culture, health, for example. There are many things. So I work a lot in this area, so urban computing. So the study of how city basically develop in space. Okay. So this is actually the first law. Again, if you took a book of geography, the first law and the most important that everyone mentioned is the Baldotto law. So the first law of geography. So anything actually is related to this concept. So everything is related to everything else, actually, but near things are more related than distant things. So there is this concept of basically proximity. So if you are here, so this is your evidence. So you can find relation between all these points sometimes, but the point is that the distance counts. So more closer is evidence or a point in this case, and stronger is the relation, right? So distance actually counts. Okay, there are many other laws. Let me go very fast. This is a very exploited one. So it's the gravity model. So basically the idea is that you have, this has been studied, for example, in migration, population migration. So you have two places, two cities. Basically the interaction between the two is proportional to the, let's say, the population or any quantity represented in this place, but inversely proportional to the distance. So that's the main concept. So it's proportional to the, let's say, population or any quantity, and inversely proportional to the distance, as so the gravity law actually physics works, almost. But the point is, when I started again. So the first thing that you do is making maps, right? But making maps, actually also Alex said it very well. So is actually the last part, right? In the sense that before you have to have a theory, you have to study theory, you have results, and then you show it, right? Sometimes I did it. I started just to take the data and visualize it, right? And this is so cartography is actually the study and practice, is a discipline as is, how to make maps, right? And we're going to go a little bit through that. So this is actually a very nice video, but we don't say that explains why it's important.
Speaking of wealth, there's so much change in terms of technology on society, on business. I'm curious, have you ever Googled anybody? Do you use Google?
Occasionally. One of the things I've used on the Google is to pull up maps. It's very interesting to see. I forgot the name of the program, but you get the satellite and you can, like, I kind of like to look at the ranch.
So
I want to be sometimes.
So this is the definition of Google Maps by a sort of former president of the United States. But the idea is that, so everyone uses maps, right? So he was basically mentioning Google itself as, so the maps as a representative of the Google ecosystem. But anyway, so maps are everywhere. So just a crash course on, so basically coordinates, just a little bit, because we need to understand. So first thing, when you have data, you get data and you have coordinates, but you have to deal with coordinates, right? It's not as easy as you can think of, right? So just few concepts. So imagine that you have the standard way to represent a point in the space, for example, in the Earth, and then you have longitude and latitude, can be expressed in many different ways, so degrees, many different ways. So you can have also the third dimension, the altitude, the accuracy of the evidence, and also the time step attached sometimes. You can reverse geocode a point and get the address if you want, so that's another very common operation. But the point is that you have coordinates, and coordinates are related to projections. That's the first thing that you have to deal with when you have geodata. You have to understand in which kind of projection the data is from. And the point is you have here a three-dimensional space that is our planet, and you have to create a two-dimensional space, right? So the way in which you do that, basically, is the definition, not very formal, but the definition of a projection. So you can do this operation in very different ways. So this is, for example, the Mercator, the one that Google Maps or any maps actually uses now. This is very old, actually, it's from the 16th century. Mercator was a navigator. Basically, this one has it's very, to say, easy to represent also digitally, because you can divide the planet basically in squares, in little boxes. So, and was used to navigate, because basically if you follow a straight line using this map, you can go from any point to any point just going straight, right? So you maintain the direction. So that's why the sailors were using this Mercator projection. But there are many others, like rectangular, some are very strange. So for example, this is not a rectangular one, so it would be very difficult to, for example, represent digitally, right, in a map, something like this. Anyway, so there are many. The main point I want to make is not like the math behind this. So the winged triple, for example, is used by National Geographic. It's the official one. So if you know already something about maps, so go read this because it defines you very well. So which kind of map basically say a lot about you. But anyway, so read after this nice comics. So, but the point is that which one should I use? So there is no a perfect projection, right? So any projection basically introduces errors, right? So there is no projection that is perfect, because you cannot solve the problem from three-dimensional space to a two-dimensional without creating some distortion, basically. But there are different kinds of distortion. So you can basically maintain, for example, the shapes of states and continents. You can maintain the area of continents. You can maintain directions or angles. So you can maintain different, dimensions of the problem, and you have different kinds of projections. So we are not going into detail of this, but basically what you can do, for example, in an active way, so there is the link in the slides, you can go to this system, is an interactive system where you can basically see how the planet looks like if you change the projection. And any of this is the 4 dimension of error that you can have, basically. So you can pick the one that you prefer, the one that is closer to your task, actually. It depends on the task, of course. This is maybe a tutorial video. Okay, so you got the point, right? So the point is that if you use the Mercator or any, so for example, the Mercator is one used by Google Maps, you have distortion. It is really, really something you have to take into account. For example, if you are a sociologist and you want to study the perception, for example, of states, right? So, for example, if you, there are many complaints about biases, basically, because you see the map and you see that Africa, for example, is very small compared to other continents, and sometimes you see a map, you see sizes, and you compare the sizes as the importance of something, right? The bigger it is, the more important it is actually in a phenomenon. So you have really to take care about this kind of stuff. So geographers don't use Mercator, right, at all. Okay. Okay. So the nice video, basically after you can look at this very nice. It's an episode of West Wing talking about maps. So anyway, so you have this data, you have projection, you have coordinates, and you have different kind of data you can analyze. So first of all, the one we are going to look at today basically is vectorial data. So it's data that is in a form of a vector, right? So they could be points, they could be surfaces. So we saw many maps about surfaces before. They can be what we call aerial data, counting polygons basically, counting states, anything like this. And they can be networks, for example. So we saw before many maps about networks, like the points and links between them. And then there is another form that is more related to raster data. That is basically images, right? So you have the vectorial. So this is a kind of image of points. For example, these are images in Instagram in New York. This is more polygons, census tract. And then here you have OpenStreetMap and all the network of streets segments. These are kind of a network. And then this is actually raster data. So the data is divided in cells, is a pixel, is an image, and this is the corresponding vectorial data. Of course, between the two you have, how to say, a different view of the same kind of data, right? So you have to be careful which kind of data you want to use. We are focusing on this one, so vectors, basically. Okay, so there are many formats. This is more related to computer science, so let me skip this. So you can have many formats for example your projects. You have to deal with at least one of these formats. So the way in which you basically use and manipulate this data is not trivial. But there is no actually time to do it now, but it's something that you have to learn actually to work actively with that. So the sources could be a lot. You can have social media, you can have OpenStreetMap, you can have administrative data, census data, any open data portal. I use a lot New York and London because they are very big. You can find many useful data, but there are many data around, mobility traces, CDRs, or anything that has coordinates. Okay, so let's go a little bit more about talking about the framework of analysis, right? So what usually I do, or at least when I started, so basically the idea is that you have a process here that creates some patterns geographically, so in the space, right? These are the patterns. So what you do, the spatial data analysis discipline does actually, is try before, the first step usually is identifying and describing the patterns, right? So you have the data, you describe it. You visualize it, you play a little bit, you do this descriptive analysis. So that's the first point. The second part is to try to identify understanding the process, right? So what happens usually is that you don't know the processes, right? You don't know the process that basically creates these patterns, but you observe the patterns, right? So the idea you observe the patterns and then you try to infer back the processes. That's the second part of the most difficult actually of all the data analysis pipeline, right? Okay, so we're basically this is what we do starting from above. This is the easiest part and going down toward the stack. And this is the most difficult part actually. So before you describe the data, more for computer scientists actually. So database, spatial analysis, relations, and then you do exploratory analysis basically. You show and discover the patterns, and then you do something that is more related to basically statistical analysis. That is basically you combine geography with statistical analysis. So you have an hypothesis, and you try to test if the hypothesis is true or not through statistics, basically. And then you do spatial modeling. This is the most difficult part. We are not going to deal with that, and Alex actually explained much more complicated way to do modeling than this. But anyway, so we basically focus a little bit on these two parts today. Okay, so let me show you a little bit what you have to be aware of when you start and analyze this kind of data, spatial data. The first and the most famous one, the pitfall, is this problem. It's called modifiable area unit problem. And the idea is it's very easy. So basically you have data, you extract some results, but these results depends a lot, in the way you aggregate the data. So if you have a phenomenon, you study a phenomenon, let's say crime in a city. So the point is that if you have points that are the specific evidence of crimes, you can aggregate this point in different way. So you can aggregate the point by census tract, borough, whatever, so neighborhood, county, states. So, and all this kind of aggregation can lead to different results, right? So because it depends a lot on how you aggregate things. So basically you have two effects. One is the way in which basically you describe the boundaries of the zones, so the polygons. And the other way is the scale effect. So from smaller scale to a bigger scale, right? So you can do different aggregation. So let me give you some examples of that. So for example, one in political science is very famous actually. So it's an effect of, it's called gerrymandering. Basically what you do, so you have a state, right? And you try to define the boundaries of counties, right? So the way in which you define the boundaries can lead to different, actually, results in political election. Actually, this is a kind of trick they try to do. And the idea is that you try doing two things. It's called cracking and packing. So one thing is you try, imagine that you have two opposite parts, right? You try to spread, basically, divide the boundaries in a way that the other part is spread around, right? And the second part is the packing part. You try to concentrate all the opponents in a single place, right? Because imagine that you have something like this here. So this is the green part, so these are votes. So if you divide like equally, so uniformly, so green in this case win, right? Because you have here the majority are green, 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 green. So all the area can be correlated by green, right? But if you divide in a different way, something like this, so doing like a specific and peculiar border, so what you find at the end is that yellow wins, right? Because basically what you clustered all the green one in few areas. So this one becomes green, but the vast majority, so the other three, this area, this area, this area, remains yellow. So basically the election are won by the yellow party in this case. Right? So actually it's something that happened for real. So these are all examples from Wikipedia where this kind of very strange shape, look at this is a county, right? It's a very strange one, right? This was a real one. So actually all of them were changed lately at some point, but these are all real boundary of county in different areas that are basically picked in a way they can basically manipulate or try to manipulate the effect of, for example, political election. So the boundary is very important. The second one is the sides of the area, right? So imagine that you see this map. These are votes, so the red one are Republicans, the blue one are Democrats. So who thinks here won the election? If you just see the map. So there are like many, look at that, red one, so it's, visually you can see that the red is more prominent than the blue one. So this is aggregation by county, right? But imagine that you do the same, and you aggregate, instead of using county, you aggregate state by state. This is the effect, right? So the map looks a bit different. So for example, look at the Washington state here. So here it looks like more red, but in fact it's more, so it's blue if you aggregate in a different level, right? So it depends on the level. So here you zoom out basically, and you have different, you can measure your statistic, your, how to say, what you want to measure actually. can change a lot. So in this case, the political election, the difference is that the system is different, counts also how many people live in the single states or county to calculate who will win at the end. But anyway, you get the point. Okay, so first of all, decide the boundary. So let me give you this suggestion. The point is that how do you select the area? So county, states, or any other way. So as we saw before, it shouldn't be driven by the data, but it should be driven by the theory, right? So you study a phenomenon, and you want to study a phenomenon in a particular aggregation, spatial aggregation, that makes sense in your theory, right? So it's not like many people actually do. You take your data, you try to, okay, let's try with census tract. Okay, the results, I don't like it. Let's try with states, if you aggregate, or I don't like it. So they keep, let's say, changing aggregation, trying to maximize what they want to show, but it should be the opposite. You basically back up by the theory, you should say, I want to study at census tract because the process that I want to show works at census tract. Makes sense at this particular level. So the second one, that is very related to the previous one, is called ecological fallacy. So basically, this is a very typical mistake that people do, at least at the beginning. So basically, you have, So here, you have an aggregate statistic. So for example, crime by state, right? Or by county, or by neighborhood, right? And then you try to basically say something about the individual. So something that is, how to say, in a finer granularity. So this is a mistake, in the sense that you cannot say anything about the individual if you have basically a statistic that is based on an aggregated level. So you cannot go down in the hierarchy, but actually what you can do is aggregate up, right? It's more coarse aggregation, but not at finer aggregation. So you cannot say anything about individual, even if you have the county homicide rates, right? Because the phenomena, the processes that moves these phenomena are different, right? Okay, so the third one is also very common. So you take a bunch of data from everywhere, so mobility, and then social media, and then census tract data, anything, demographic one, but they have different aggregation. So one is by county, one is a point, another one is by state. So what you should do in this case, so this is a typical example, when you have different kind of aggregation, what usually you do, you try to aggregate to a common scale that is the finest possible, but it has to be shared, right? So it's the finest possible aggregation that you can find that is common to all of them. But this is a kind of a problem that you have to take care of when you have different multiple sources. Okay, so there are many other critical issues actually. So for example, one is, that we're going to see later is called the spatial autocorrelation. It's one of the main concepts here in statistics, spatial statistics. Basically, you have a location, a point, an evidence. So the point is that the points that are around this evidence, usually, there is, so they are not independent. So that depends from actually the first law of geography, so anything that's closer is more related. So the idea is that usually there is a correlation between an evidence, some phenomenon, and the one around, right? So for example, why this is a very important point, because if you do like some regression, for example, right? So you have your variables, some are spatial, some not. You do your regression, you use the standard methods for doing regression, right? If the data is spatially correlated, basically you are making a mistake, because so the standard regression basically theory said that the evidence are independent, right? But if they are spatially correlated, they are not independent. So you cannot use the same method that you are using before, the non-spatial data, if you have spatial data. So you have to use specific methodologies that take into account the spatial component. So different methods. There are many of them, but that's a very important one, right? Okay, so another one is called edge issues. So basically you have your map, you study a phenomenon just in an area, right? What happens to the evidence that are at the border, right? So at the edges of the study. So why is important? Because if you study, for example, autocorrelation, so you study basically the relation between the point and the neighborhood, But if you are at the edge, you don't have neighborhood, right? You have just one side, for example. So there is lack of information. So what you calculate at the edges could be very different from what you calculate, for example, in the middle, but just because if you are at the edge, you don't have complete information. So that's another thing that you have to take into account, especially if you aggregate. So you have all the evidence, also the edge one, you calculate your statistics, you aggregate, you do an average, for example. That's a mistake, because the edge one, for example, have different behavior. Okay, so let me go very quickly, even if I really love mapping, so I can talk about mapping for hours, but this is not the case. So we saw already many beautiful maps animated before, but the idea here is that before they were studying this kind of maps. This is what the typical geography map look like. It's like a reference map, you see states, or if it's a natural one, mountains, rivers, and stuff like that. But what you do actually for visualizing data is the thematic map. So you have a phenomenon you want to show on top actually of the reference map, and you show distribution of data in space. This is called thematic map. And this is a lot of theory that is a mix between human-computer interaction, visualization, how to display data. So it's a big area of study actually. But the point here is that you use thematic map for showing a phenomenon, so a distribution on the space, and the point is that maps can lie. So that's the most important part, right? So you show a phenomenon. I'm gonna try to let you understand very, how to say, strongly making the point that maps, if you don't interpret very well maps, they can basically lie and say something that is not real, right? And let me give you this example. So let me skip a little bit more quickly. What time is it? Okay. Here, these are the typical maps we do. We use to visualize, for example, points. You have distribution, you have a value related to a location. The bigger is the point, so bigger is the quantity you are showing. Another one is the dot distribution, the distribution of density of the points basically inside the space. The isoplate, we saw some isoplate before. These are more aerial data, so these are surfaces, it's not points. So it's a polygon. This is the most famous one. Sociology, political science, every paper now has one of these, right? Corporate. Cartograms are a little different, so they modify the shape. And the flow map, we saw many flow maps before, so they show interaction, movement, so network-based data. Okay, let me go a little bit faster because I don't have time to go deep into these elements. You can find in the slides all the reference to theory and examples of all of them. This is, for example, if you have many points, you can cluster them, for example. You can do aggregation using hexagon instead of grid, if you want. This is, for example, one of the most used and misinterpreted way to display data. So this is just a density map. It's called heat map. Okay? So if you have points, you can aggregate using a kernel function, actually. Different kernel function can give you different idea. But the point is that you are just showing density of points, or density of a certain phenomenon under study, right? And this actually can lead to many misinterpretations. Let me give you this example. So this is very funny, comes from, say, Thomas' line before, but let's say this is a map that shows density of use of a website. This is a map showing density of, I don't know, subscriber to, this is another website, I think. This is consumer of pornography, whatever, but they look like the same, right? Why they look the same? So these are they have the same density just because the population, right, clustered in these particular places, right? So they don't show anything, right? They just say here that here there are areas where people cluster, live more, right? So be aware that this kind of density function are a little bit difficult to interpret sometimes. So these are the isoplate if you have a continuous phenomenon instead of discrete data. This is actually the one that many social scientists, computer scientists, if you read papers, you can see something like this. The choropleth, so this, each area is colored by accordingly to a certain, what we call classification schema. So you have your variable, your data can be continuous or discrete, and then you basically, the higher the intensity, in this case, the darker is the color, for example. But there is a very, very important concept here that I wanted to stress. Okay, it can be categorical, continuous, that if you have continuous data and you want to show a choropleth map, you have to basically transform continuous data in discrete data, right? So for example, if you take 5 classes, so you have 5 colors in your map, so how you do this transformation? How you transform a distribution in a set of buckets, basically. So you can do that in different ways, and this leads really to a different visualization, right? So for example, if the data, let me jump straight to the point here. So if the data is normally distributed, you don't have many problems actually, because you can use different classification scheme. You can use, for example, equal intervals, divide each interval of the distribution, so for example, the range in equal buckets. The quantile, each basically buckets has the same number of evidence. Standard deviation depending on the standard deviation, so 1 standard deviation, 2 standard deviation, 3 standard deviation from the mean, and stuff like that. So all these maps look almost the same, so they are consistent just because the distribution is kind of normal. So if you use all of them, it's not that you have like completely different results, even if here, for example, you can say that it's more smooth than what you can see here. But the problem comes when you have this, that is a very skewed distribution, right? So here you have a lot of values that cluster in this area and very few values in the tail, right? So for example, if you use equal interval, this is the result. So you basically don't see anything. You see a map colored by, so the low part, so this value, so the low part. So this basically doesn't tell you much. The quantile works actually a little bit better because you take the number, it's based on the number of evidence. But it's very important how you pick the different classification scheme in order to interpret this map. So when you see a map and you don't see the classification scheme explicitly, this is a bad map, right? It has to be very clear how you basically classify the data in classes. So there are more examples in the slide. You can go through all of them. Okay, let me skip a little bit. So these are all the type of maps you can do. So this is a very typical map we saw before, the flow maps. These animations. With maps, actually, as we say, you can lie. So let me give you this simple example. You see this representation. Do you think these patterns, spatial patterns, pattern is random or not? No. This is not random because it's clustered. So basically, squares that are close each other, they cluster spatially. So if I see this, it's random. Who say yes? One yes, few yes, no? Who say no? Many no. Okay, so of course, what I just tried to demonstrate to you that even just looking at this pattern, this image, you have different interpretation, right? But the point is that this image is not random, right? Actually, it's spatially correlated, but in a different way than before. So in the sense that this is clustered, this is clustered, and this is what we call dispersed. So each point, so the neighborhood, has values that differs a lot from the value that you are taking into account, right? So for example, here you can see, this is very low, this is very high, this is very low, this is in general high, right? So this is not random. So the random one is this one, okay? So, I mean, again, so if you visually inspect data, you cannot really tell if something is random is clustered, dispersed, so you cannot really tell what's happening. Okay, so the point of this point of the first part is that you can do like this kind of, is called descriptive spatial statistics. You have your data, you calculate many metric, it could be the center, the centroid of the data, and many others that are in the slides if you want to go through all of them. But this is just the first part. It's just to understand what you are looking at, right? So you visualize them, you do the mapping, but this is not enough. You cannot stop here. So that's what I was doing before, actually, at the beginning. I was visualizing, doing like super cool things, but then you basically have not the complete pictures, right? So in this slide you have many metrics you can calculate from spatial data that you can look at. So mostly related to centrography, it's called, or measure related to dispersion of points around the space. There are different ways to calculate them. So I'm not going through all the details, but these are very useful and descriptive metrics. You can use density curve estimation. This is the heat map, actually. It's the same thing. But the point that you have to do something more, right? So the bits that you can do, you have to do after this part is related, strongly related to statistics, actually. So it's called spatial statistical inference. So you take all the concepts from standard statistics, statistical inference, so the concept of population, which parameter, the sample, the sample statistic, hypothesis testing, so anything that comes from statistics holds, right? And we want to do the same in the field of spatial computing, right? So how we are going to do something similar? So the idea, the basic idea of hypothesis testing in the spatial field is that your null hypothesis is that anything is random, right? So you observe a phenomenon, and the space really doesn't matter, right? So the point is that if you have this hypothesis that the phenomenon is random spatially, that's not really interesting, right? So okay, it's random, but you cannot really tell anything about work. So we are interested actually in something that is not random, right? So this is actually the null hypothesis, and usually what you want to prove or you want to show is the alternative hypothesis that usually is something related to how the pattern that you are studying is far from random in different ways. As we saw before, it could be clustered or it could be dispersed. So it could be that it's far from random in the opposite way. So different values go close each other. Okay, so how we do that? This is visually, again, another example of randomly and spatially clustered. So here the point is that once you do this, and I will explain how we do that. For example, you show that bank robberies are clustered, right? So you have this evidence, you prove it. We're going to see, for example, using auto spatial correlation metric, the Moran auto spatial correlation, but then your work is not over, right? You just show a pattern, but you want to try to understand the process. And the process can be different, right? So imagine that, I don't know, all bank robberies are clustered together. What does it mean about the process? It can be, for example, that all the banks are clustered, right? So the robberies are clustered because the banks are clustered. This is actually due to proximity, so as a proximity effect. This is called second order effect, actually, usually. And this is an influence process. So basically you have an evidence of a phenomenon, and this evidence influences the close evidence, right? So this is an influence effect that you can model, we saw before, but anyway, so this is a different phenomenon. But the point is that if you look just at the pattern, you do statistical inference, you cannot really tell if you have just cross-sectional data, so data that show just a snapshot of your system. You cannot really tell which one is it, right? It's very, very hard to tell which one of these effects is in place. You need to have temporal data. It's a kind of more complex way to do it. But what usually people coming from geography and statistics they do basically something like this. They have this null hypothesis of complete randomness. They try to prove the alternative hypothesis. And the point is that sometimes, to prove that, as you do in statistics, you can calculate, for example, a metric, a sample metric, and then what you try to do is you can infer analytically the form of this metric in relation to the space, basically, so you can calculate the real formula. And then you can see how your evidence, what you see, so your sample, differ from the distribution, this formula that is based on the randomness, right? So you have your formula, you calculate the formula, the expected mean, the expected standard error, and all this stuff. You have your sample, how they differ, and you can say, okay, I can reject the null hypothesis or not. But sometimes it's very different. It's very difficult to do that, so analytically derive this distribution. So what they do actually is doing a simulation approach. So basically what they do, you have a phenomenon, you just randomize many times, you do randomization. So you randomize, you shuffle all your spatial distribution, and you measure the metric, and you build a distribution that is based on this kind of repeatedly simulative experiments. Right? So you simulate, you build the sampling distribution, and then you see if your evidence, how far is your evidence from the sample distribution. So we use like very often this randomization approach. So let me just go to one of the main concepts geography and statistics, and the spatial autocorrelation. So how we measure this kind of clustering approach. Okay, so why is important? We already discussed many times. Why is really important is an important phenomenon, but how we do that? Okay, so the first part actually is not as easy as it looks like. So the first thing that you have to understand is how elements are close to each other. So which is the definition of proximity, right? So you have an evidence. So how you calculate which one is the closest? So the neighborhood, right? So you can do it in many ways. So if you have points, for example, you can calculate a grid like this. So you have here your evidence. So you can have a rook, for example, it's called rook. Way to calculate is like playing chess, actually. So your neighborhood are this one, this one, this one. Or you can use a queen way to calculate proximity. So you take all your neighborhood, so the yellow one here. You can use first order, second order, so the neighborhood of neighborhood, and stuff like that. So the point is that it's not easy to understand how contiguity is calculated. So how do you define neighborhood? And in geography, they do it in many ways. For example, here for polygons, if you have irregular shapes, it's not very easy, right, to understand which one is contiguous to the other one. Sometimes you have very different shapes, very different way to do it. But you can do it with like tools. For example, this is made in R. So how do you calculate proximity? So for example, here it takes into account proximity and distance. So you can see, for example, that Russia is close to the United States to Alaska, for example. This is a band of 500 kilometers, I think. So contiguity, distance, and then you have another approach is the key nearest neighbors. So you pick the closest neighbors. You can be the first one. You have something like this, or you take two. So it's neighborhood of neighbors, or you can have five nearest neighbors. In this case, you have a more dense and connected area. So the point is that whenever you can pick one, depending, of course, of your theory, what you are basically trying to study, and then you can calculate a matrix like this. It's the weight matrix. So this is your evidence. This is a weight that say, for example, here is the evidence ij. So it could be binary. So basically, these are neighbors or not. So these two I and j, or it can be a number. It could be based on the distance or anything else. So you have many ways to do that. So what usually they do is to try to calculate a weight that is row standardized. So basically, the sum of each row is 1. So that's a typical thing they do. But anyway, whatever you pick, what you have to do, you have the proximity. And then the first thing you can do is to calculate a global measure of correlation. So a global measure means basically this is the value of how clustered or dispersed is your data globally in all your area of interest. And then there are local measures that basically says you are a single element, a single unit here, and you calculate the same metric for each unit, and then you have a value of how clustered or dispersed is the single unit with respect to its neighborhood. But it's not aggregated, it's not average, right? So you have local measures, so you can do both. So, okay, so let me just introduce this Moran-I statistic, that is the most famous way to calculate autocorrelation in spatial data. So what you do, you have points and polygons. You can have both. This is just a formula, but I don't really, so it's not very difficult formula. So this is kind of similar to the Pearson correlation. So actually this part, and also this part. And then is mediated by the weights, right? Here. So basically it has two components. One take into account, so the proximity part is that part. And the other one, how different are the evidence with respect to the mean. It's a kind of Pearson correlation that takes into account also the distance in space. So but anyway, so if you have standardized law, you can have a little bit easier form, but that's not the point. The point is that once you calculate that, you can basically show, for example, this is the typical scatter plot they do when you have, for example, in this case, is poverty in an area, so by county, for example. You have all the counties, or neighborhood in San Antonio, and then you want to calculate if the fact that an area is have a certain value of poverty is related to the neighborhood, right? How, like, actually, how much poverty there is around, right? So this is the typical way they show it. Oh, sorry. So this is poverty rate over the poverty rate of the neighborhood. Like the poverty rate means basically the poverty of the neighborhood. So this basically says, so you have your value more than I, calculated like before, 0.6, and this shows basically that it's clustered, right? So this trend, so this the slope of this line is exactly actually this value diffuse regression, but that's another point. So what this shows that there is a positive correlation. So high value clustered together, low value clustered together here, right? Okay, so each of these quadrants means high, low, high, low, low, high. So here you have more points than here, for example. Okay, but that's not enough. So you show that you have this autocorrelation, this is a value, but you didn't really show already that this value you get is statistically significant, right? So it's something that you wouldn't get if the data was random, right? So you have to prove that. And the way in which they do, this is another example. Okay, you can do bivariate. So this is poverty rate and another, for example, crime rate over the neighborhood. So you have two variables instead of one. That's already what they did. But okay, so what they do in practice, I don't think I have a lot of time, so let me jump a little further. So you basically calculate the Moran-I, so your metric, using this kind of permutation test. So you have all the value of your data, you do a lot of permutation, randomly permutate. Every time you calculate the value, you build the distribution, so your distribution of values, and then you have the one that you measured, is 0.6 before, right? That we took before. So you have your distribution, you can calculate the p-value, and this is actually a pseudo p-value. This formula, so you calculate the pseudo p-value, and you use the p-value as you were using the p-value in the standard statistical inference. So you say, okay, you can interpret the value as, for example, 0.1%. There is 1% probability that you will be wrong if you reject the null hypothesis. But anyway, so you take your pseudo p-value and you do your inference, right? So for example, let's say this is the distribution of all the value of your statistic when you do randomization, basically. This is the shape, and this is the one you measure. And as you see here, is outside the distribution, right? So this is under the null hypothesis, and this is one that you observe, and the distance is statistically significant. So in this case, usually you can prove that what you were studying is really autocorrelated. So, but then you didn't see anything. So basically, if you have that, you cannot tell if so you have spatial autocorrelation. You cannot say that if it's a cluster effect, so high value clustered together, or is that dispersed effect, right? So low value are close to high value. So that's another part of the analysis, actually. But anyway, so what you can do here, you can do visualize. This is another example. This is uncorrelated data. In fact, the sample is inside your distribution, so you cannot tell it is different, so you cannot reject a null hypothesis, for example. There are many other measures, vagaries, there are many other, usually we use, or geography. In geography, they use a lot of more than I, for example. But there are many others. So let me just close with I think the last one that is related to the local version. So basically here we have studied the effect on the global. So all the area under study, you study the autocorrelation. We want to study locally what happens. So for example, if there are clusters of hot spots or cluster of low spots, right? So for doing that, you can calculate it's the same idea than before, but using local measure. And local measure is something like this. For each evidence, for each I don't know, county, for example, you calculate the Morani following this formula. It's the same than before, almost takes into account the weight and the difference from the mean. This is the standardized form, but besides it, it's not very important now the formula. But the idea is that you have a value for each aerial unit, right? For each of them. So what you can do is the same that we did before. And you plot them. For example, here is the local Morani in this area. So the red spot here, these are the value high. So basically where high value cluster together, and this is the value where you have low local Morani. So high Morani, low Morani. So basically, you can take the same picture, you aggregate everything, and you have one value for all the area. Here, you have different value for a single area unit. But the point is that even if you have a high value of Morani, for example here, this can be not statistically significant, right? So it doesn't really tell you anything if you have a value, for example, high value, if this value is not statistically significant. So what they do usually is to calculate the significance for each element. So you can replicate the same thing we did before for each metric here. And then you have something like this here. So all this white part here, these are all the county or the area data that is not statistically significant, right? So I don't really care if it's high or low. You cannot tell anything about that because even if it's high or low, it's not statistically significant, so it's completely useless and it leads to wrong actual results. So the only one you can tell something are this one, and these are the only one that basically are statistically significant according to the area before. Then when you have this, so you just inspect this single area and you try to understand if it's positively correlated, negatively correlated, and why this is happening, right? But that's one of the common mistakes. So just taking the number without studying the significance. Okay, so there's another example with a tool that I suggested to use. It's called Geoda, and it basically gives you all the pipeline of this analysis for free. So you take the data, you put the data inside, and they calculate the local Moran, the global Moran. They do the scatter plot, they do the statistical inference for you, and basically they tell you these one are not statistically significant, these are a cluster of high value, low value. So you can spot the hot spot and the cold spot, for example, for your biology. So this is completely automated, so you can use software like this or R, Python. So there are many ways to do this. So here, actually, we don't have time for doing regression, but the only thing I just want to say probably is that, again, if you want to do spatial, so what to do regression, you cannot use the standard way to do it because your evidence are not independent, right? Because if there is spatial correlation, there is correlation, they are not independent, so you have to use different models. There are many around, so I can tell you exactly, for example, the packages in R that they do this kind of regression using spatial models. Okay, so let me, do I have like 10 minutes more? Yes. So let me just give you a little bit of an idea of which kind of application or where we can use this, all this kind of pipeline of data analysis. So this modeling of the data, so basic description of the data, and then you try to find patterns, and then you try to basically doing statistical inference, see if these patterns are statistically significant, and then basically do regression, and you try to understand the why. You don't do much modeling, but there is also a lot of modeling going on, and Alex showed that we did before. But the point is that how you can use this, right? Where? So which is a possible application. So this is a totally different area actually. So where I kind of work. I worked in the last few years, and let me give you just an example very quickly. So, no, it's not showing. No. Okay, I don't know why it's not working. It says okay, let's do it without slides. That's okay. Okay, so basically the idea is try to study cities basically through digital data, right? So you have all this kind of data, spatial data. It comes from different sources. So you have social media data, we use a lot of social media data. We use data from census data, any kind of data, mobility data, CDR, so phone calls, a bunch of different heterogeneous sources. And the idea is that try to understand which are the phenomena that regulates, for example, the life of all of us in a city, right? So there are different aspects of that. So for example, you can use this for doing so more in the architect's point of view, to design cities. So how you design the space in a city to make the city, I have to say, more livable, so or closer to what people like, so make people happy, for example, or how you design spaces to make people healthy, or any kind of things related to humans, right? So the other approach is try to more computer scientists or more from engineers, how you basically create the city is more efficient, right? So you try to model mobility in a way that you can go from one point to another point as fast as possible, or you can basically minimize the use of water, electricity, anything related to resources that are limited, right? So it's more an approach, try to make it efficient, right? And then, so you can study more related to computational social science, you can study social phenomena, because cities are aggregation of people, right? So you can study social phenomena in the context of a city, right? So how people relate to each other, how people socialize, how people, I don't know, buy things, or they go around, they do anything related to social interactions, right? So these are different areas. So what usually the last years actually I've been working on is trying to use data coming from social media, basically. Imagine that you have a picture, right? So like an Instagram picture or a Flickr picture or anything that is a visual content. And this element has attached coordinates, right? So these are not precise, there is a problem of accuracy, there are many problems of bias, many different kind of elements, but the idea is that you have these pictures, that there's a content, right? So with visual inspection, automatic, like deep learning, this kind of thing, you can analyze, for example, what's inside a picture, objects, or you can even analyze emotions, you can analyze many things from the visual part. So you have the content, the visual aspect, you have metadata attached, location, tags, textual information, anything else. And then this is a very powerful source, right, of information. Why? For example, what we did is a kind of a very different and strange thing to study, but is senses, right? So for example, you are in a city, you are on a street, right? So you walk around, so which is your perception of the environment, right? So for example, in terms of sensorial experience, what you see, for example, how beautiful is what you see, or what you smell, or the sounds around you, stuff like that. Since of course, what you can do is measure things. You go around in the wild, and you measure sounds, you measure smells, you measure how beautiful it is, even if beautiful is a kind of a tricky concept. But anyway, you can measure, but this is not scalable. You cannot have people going around and measure things. So what we try to do is to use digital data as a proxy for this kind of elements. And the goal is to build basically a interactive, dynamic, almost real-time idea of perception. So the perception of the humans in a space, right? So the first attempt was using the visual part. So it's the sense that you use the most, right? What you see, you go around. What you see really affects your emotional space, right? So what we did is you take images, you analyze the images, and we had actually, through a crowdsourcing game, we collected a bunch of basically annotations saying you have an image, 2 images basically, which is the most appealing or beautiful, right? So you play this game, and you say, oh, this one is more beautiful, this one is less beautiful. So you have different scenery in the city, right? So if you have thousands of people playing this game, and of course in certain conditions, so in the sense that there is no bias in terms of weather or time in the day, stuff like that. But anyway, so you can aggregate all the points. So all these images are coordinates, right? So you can aggregate these points and you say, basically, in this part of the city, the perception, the visual perception is, like you say, more appealing than in other parts of the city, right? So you have this map that is weighted by beauty, let's say. Or you can have, so how you rate how beautiful is a place. That is not the same thing as a beauty. But anyway, so you have this map that is weighted. So you have the map of the geography. So what we did at the beginning is just a way to change the pattern of movement, right? So how do you move in a city? You go from a point A to a point B. You go to Google Map and say, please Google Map, give me the path between A and B, right? So if you do that, it gives you basically the path that maximizes the distance, or it could be time travel, or anything related to efficiency. So what about if you weight this kind of path you have to go through, instead of just using objective measure, you use also this kind of layer that tells you how beautiful is a place, or how beautiful is perceived. So the idea is that you can go around, changing a little bit your typical route, and have a completely different experience instead of going through, I don't know, a street that is very traffic, packed with people, or perceived as stressful. You can go just in the street that is, I don't know, just the parallel one that is more calm, maybe has like trees, or maybe historical landmarks, and stuff like that. So this is just an example of how, instead of using just the criteria of efficiency, you can use also the criteria related to more a human perspective. So this is called, we call it happy maps. So it's like the way in which trying to let people be a little bit more happy going around through the city. And then we realized that it's not only what you see, of course, and we started to study this map. This is kind of a strange thing, of course. It's a bit a strange topic, but so we try to analyze which is the smell perception, right? The problem is that urban, so if you go to a city council, actually people don't care about smell, or actually they care about smell just when it's a bad smell. So trying to manage the management of bad smells, basically. But the point is that there are also good smells, and then this sensorial layer really affects your emotion. So the nose and your emotional state are very connected. I'm pretty sure that you can have many examples of that in real life, right? So how you have a bad or positive reaction to smells. So basically you have this layer of visual perception. You have another layer that basically tells you the smell perception and also the sound perception. So the sound is what you hear basically on average if you go to a street, right? So what you can do is basically use this multi-layer network where each location has different coefficient, and each coefficient is weight is related to a sensorial perception. If you add to this many other dimensions, that is not, of course, is not only about senses, right? There are many other perceptions that relates to the real mobility of people, or what the activity of people, what people do in a certain area. You can add actually different layers that can lead to a different way to move around, for example. Okay, the last thing I want to mention is the last thing we are doing right now is we moved a little bit from this sensorial mapping. Always using digital data, we are trying to relate, for example, health issues and problems with the consumption of, for example, of data coming from Tesco. In London is a chain of supermarkets. So basically we have very fine-grained data about what people buy. So what kind of food you buy, actually, right? So, and you have the exact every day for consistent portion of people, let's say almost the totality of people that goes, of course, to Tesco, all the data of what they bought. We have health data, so basically you have all the official data from the health department, so which kind of disease occurs, so how many times you go to the doctor, which kind of meds you take, all this kind of data. So the idea is that we want to try to correlate this kind of health condition at neighborhood level with the consumption of food. And these are many implications in terms of, okay, for example, the first thing is, of course, you can see some neighborhood, depending on social demographic conditions in terms of what they buy, they have very different metric in terms of health conditions. So their neighborhood, they are more healthy, and usually are related to what they buy and which kind of people live there, right? But you can do that in pretty real time, so that's the cool part. So this map is actually interactive, and you can explore in time and space how what people buy and how it's related to the health outcome. Okay, so just to wrap up, I hope just I give you a very high-level overview of what are the possible steps, just like a very few, but very narrow idea, but possible steps starting from getting the data, analyzing the data, showing the pattern, and then demonstrating the patterns are real, and then some real application where you can use them in real life, something that is for everyone. Okay, so I think it's.
Thank you very much, Ross. We have time for a few questions. I guess everybody is ready for lunch, but
Yeah.
of course, Rossano is going to be here all week, but still. Any questions? Comments? Don't be shy.
Yeah. They are hungry.
You have one there, okay?
How much of your data is open and how much of it is proprietary? And if you have worked with both, what's the quality difference between the two?
Yeah, that's a good point. So basically lately, when I mention all this social media data, of course, some of the data comes from open stream. For example, Twitter, there is like a public stream. There is a public API also for other data, but actually this is mostly company data, right? So we use the images and we had the snapshot of all the pictures because we worked in Yahoo, and Yahoo basically owned Flickr, so we have the complete data. So it's not completely open, actually. So that's it's true that basically some of them are proprietary data. For example, mobility data sometimes is not available, it's not openly available. So some of these data are not open available, but some of them are. So for example, all the data that comes from this open portal, so we work a lot with London and New York, but any other city, these are completely open, but they don't actually have the granularity that you can have from proprietary data, for example. So that's, I guess, is the main issue, is the main difference. So with the data coming from, for example, a stream like Flickr, you have the exact events with a very fine granularity that is very hard to find in other kind of settings. So what you can have is the sample, but the point is how representative is the sample. There are many issues. So you can have the sample from Twitter, but you can do a lot of work with that, but of course there is a bias and representative issues. Yeah, so, but lately, for example, also the Tesco data is proprietary. So it's true that many of them comes from companies. But that's
what about the health data? What about the health data?
No, the health data are open in the sense that you can go, there is a portal in the health department in London, actually in England, in all England, so you can download all the data that is freely available.
And which level of accreditation?
That's a good point. So, okay, it depends. So for London, for example, we use the LSOA, this large super area output area, whatever is the name. So it's that kind of a little bit, it's just small enough. It's not big, it's not a borrow, it's a little bit like smaller. But I think this is the level of aggregation. Of course, it's not at the individual level. It is aggregated data, of course, but it's finer enough to say it's nothing more than just at borrow level.
Okay, please. Maybe the microphone, please.
So are you going to correlate just food consumption with electric data, or are you planning to add also some other aspect, like, I don't know, pollution or
Yes.
something else?
No, you're totally right. So it's not just about, yes, so there are many confounding factors, of course. So we are basically studying many different, so environmental data. So imagine that you are in a place, of course, pollution can be one. So or exposition to certain threat, for example, if you live close to an industry, for example, or kind of source of any kind of chemical emission, stuff like that. So as always, is an aggregation of different levels, right? So it's not just a few levels, but you have to study all the factors that can, of course, relate. So it's a mix of different sources. It's not just social media, or not just consumption. What you buy, what you eat. Crime data also.
Let's thank Rossano again, please.